For several years, we were interested in coral biofluorescence. It was originally found in a jellyfish. Corals are very closely related to jellyfish. They're both phylum Cnidaria. So we did an extensive study of the Great Barrier Reef, and it was just a few years ago that this eel jumped into our photograph. We say we got photobombed by this eel, and then we went on an eel hunting expedition to find this little eel. It's about the size of your finger, a small reclusive collapsid eel. And while we were searching for that eel in the Bahamas, we found about 20 other biofluorescent fish. Bioluminescence is like a firefly, so an animal that gives off its own light. It's expending an energy and it's producing photons of light. Biofluorescence needs light for it to absorb and give off, so it doesn't just produce its own light. In order to mimic the light of the ocean, you need a very narrow band of blue light. The ocean acts as this beautiful filter, so for us to recreate the ocean's blue light, we have to spend $1,000 for a tiny little filter like this. We designed these lights at the John B. Pierce Laboratory at Yale University, made everything from scratch, the prints, cut the metal. All set? We did it. We wait till the sun goes down, we drop into the reef. We don't want to look at the blue light that we're shining, because we only want to look at the light that's being absorbed by these different creatures and then given back off. So we filter out our blue light. It's just beautiful being down there and visualizing this. We had a surprise finding of fluorescence coming from a stingray. And this was really fascinating for us because if it's in the cartilaginous fish, that we thought maybe it's also in sharks. This had our brains ticking about where to go look and what groups are having this property. So we set off to the Solomon Islands on a National Geographic weight expedition. And we wanted to film this in really high resolution, so we filmed it with a Red Epic 5K camera. And we found many, many more fish. We filmed them in their natural environment. We started to see that some were using this as a camouflage, or they were red and they were sitting on red photosynthetic algae. They have these filters in their eyes, just like we put in our camera to filter out the blue light. They have the ability to see this. So one hypothesis is, on a full moon night, the moon hits the ocean, that translates into blue light underwater, and they would be able to see and recognize each other, mate very quickly, go back under their holes. We're just starting to tune in to their universe, this covert world of fish biofluorescence. We did swimmers out almost every night, scanning the reefs. We used the submarine, and this summer we're going to use it in conjunction with a one-person submarine called an exosuit. We could stay down for 6-7 hours at 1,000 feet, just working, studying these animals. And overall, we've now found over 200 species of biofluorescent fish after scanning several thousand. So my laboratory here, we're interested in studying, the biodiversity of fish and corals. We're interested in knowing which species have it, how diverse it is. We even look into the molecule itself and look at the molecular evolution of these fluorescent molecules. And on top of that, some of them we're developing into tools for humans to use. Fluorescent proteins have turned out to be one of these incredibly valuable tools for researchers and led to advances in cancer research and Alzheimer's research and AIDS research. And now we're finding new ones in fish, which we haven't even begun to characterize yet. On this last trip, we were also working with a 3D IMAX rig where we took 2 Red Epic cameras and we have them in a case in about a 500-pound housing that we would lower off the crane into the water. And we began shooting 3D biofluorescent footage for the first time. So we're hoping to assemble this into a movie that'll play at the museum and IMAX theaters in the next year or so.